Okay, I start chapter 3, second order differential equations. Here something like this. So we have pt y double prime plus a q t y prime plus a something r d y equals a s t, something like that. So if I divide, and I'm assuming that this is not 0, so divide by pt, we get something like this, y double prime plus pt, that's small pt, y prime, plus, let's see what double uses, qt and gt, plus qt y equals gt. Okay, so by dividing by the coefficient of the first one, y double prime, we get something like this. Okay. So let me write this in operator format. So this one is d squared dt squared. This one is pt d dt, and this one is simply qt times 1. And this applied to y, t gives me g. So this is a linear operator. Well, let's call it something like d2, say. Okay. So we have something like this, d2 of gt equals, so yt equals gt. Equals gt. So this is an equation. Let's compare with ax equals b. Well, A was a matrix. So, and remember this matrix corresponds to a linear transformation. Now this is also linear. D2 is linear. D2 is a linear operator. Why is it linear? Because each one of them is linear. This is linear, linear, and when you multiply by a constant, well, that's not the constant, but the function, it stays linear. So this whole thing is a linear function. And remember what we did was for ax equals b, we first solved this, homogeneous, and that gives me a solution, complementary solution, and then we solved this. Just find one solution. So x specific solution, whatever we call it, x say s or something. So, and then the whole solution was this one plus this one. Okay, so here we do the same thing. First we solve the homogeneous system. Then if I have something on the right hand side, which is this function gt, then I will find one solution. When I have gt on the right hand side, then I put them together, and that is the general solution. So let's do it. Let me erase this thing here. So I have this situation, b2 of yt is 0. And this is 0 function, in fact, 0 function. Right? Okay, so First of all, let's, as a linear operator, this gives me what? So solution space of D2 YT is a subspace of the space that D2 is applied to. Well, we can take the space of all functions that are infinitely differentiable and things like that, but let's assume that it is some kind of function space that it is applied to. So first thing is to study this solution space and see what it looks like. How many, is it finite dimensional? If finite dimensional, well, if it is finite dimensional, then that's good. In fact, if it is finite dimensional, we can find the two, or the, well, it is two, in fact, but anyway. So we can find a basis for that. So now the first thing, in fact, the first theorem is this. The first thing is so the first fact, and I will prove this fact, any three solutions of D2YT equals 0 are linearly dependent. Okay, so linear dependence and independence for functions, well, the solutions of functions is what? Is related to the Wronskian. This means I, E, if y1, t, y2, t, and y3t are solutions, then the Wronskian of these three at t is 0. Okay, so we have to prove this, that if I choose three solutions, just any three solutions, then I have to prove that the Wronskian of these three is 0. So let's write down the Wronskian and see what we can do. So the Wronskian for these three functions is the determinant of this. So let me just write the determinant. So y1, y2, y3, y1 prime, y2 prime, y3 prime, y double. Okay. Remember, if I multiply a row and add to another row, it doesn't change the determinant. So let's do it. Let's multiply some rows of this with some constants and add to another row. So, well, let me write down the equation. The equation was this. The equation was y double prime plus p t y prime plus qt was, and qty was 0, right? So this means since y1, y2, and y3 are solutions, it means that y double prime e t y prime I plus q t y I is 0 for I, 1, 2, and 3, right? So each one of them satisfies the equation. Okay, well, what do you think? If I multiply the first one, this row multiplied by qt, right? This one by pt, then add to this. So this is what I'm doing. Row number 1, QT times row 1 plus PT times row 2 plus row 3. And this goes to row 3. But that doesn't change the determinant, right? So QT times the first one, PT times the second one, and add those two to the third row. Okay, let's see what happens. Well, so that equals, let me write the third row first because that's long. So that is y1 double prime plus pt, y1 prime plus qt, y. Then y2 double prime plus pt, y prime plus qt, y. And the third one is y3 double prime plus pt, y prime plus qt, y. And the rest of them are stay the same. So this is y1, y2, y3, y1 prime, y2 prime, y3 prime. Okay. Well, these three are 0. y1, y2, y3 satisfy the equation. So the, I forgot the 3 here. And the 2, so there's a 2 here, 2 here, and a 3 here. So each one is 0. This is 0, 0, 0. The three functions satisfy the equation and they are 0. So what happens? The determinant is identically 0. One row or column 0 means that it is identically 0. Okay, so y1, y2, y3 are not linearly independent, or as they say, linearly dependent. Whatever. So it means that the solution space of this equation can't be three-dimensional, because we cannot find three linearly independent vectors or functions that satisfy this equation. So it should be either one-dimensional or two-dimensional. If one-dimensional, one-dimensional means if I find just one function that satisfies the equation, then that function gives me the complementary solution. Two functions means if I can find two functions that satisfy the equation, then those two functions constitute a basis for the solution space, and that gives me the complementary solution, so, or the solution to a homogeneous system. Okay, let's erase this thing and go back to the equation and look at it more carefully. So the equation is y double prime plus p t y prime plus q t y equals 0. But let's first solve this the equation with constant coefficients. Okay, so constant equation, constant coefficients. Well, I would write something here like a y double prime plus b y prime plus c y equals 0. And there is a reason I keep this a here, and we will see. So, if I look at this just by inspection, I can see that there is a relation here between a function its first derivative and its second derivative, and they are multiplied by some constants, and that when we add them, we get 0. What function really has this property that its derivative and its second derivative are, because they should look like the first one. Why? So these two should look like this one, so they cancel out. So if I write, say, a polynomial here, say x5, then this will be x4, then this will be x3, and x5, x4, x3, when you add them, you don't get 0. So what function or functions have this property? Well, the only function that comes into my mind, well, you can think and find something else, is like e to power x. Because the e to power x, e to power x, e to power x, the derivatives are basically the same. So it should be e to power x and the family of e to power x. And it can also be a complex exponential. Now, what is a complex exponential? So, a complex exponential is this. Now, e to power x, this x is real. So, x is a real function. This function is defined from R to R. But I might have z here, which is a complex number, e to power z. So, this is from complex numbers to complex numbers, right? And so I have to somehow find a nice formula for e to power z. But I'm not going into complex analysis or complex variables. I mean, that's way beyond this course, but at least it's, let's study this e to power z and see what it looks like. Okay, so my next goal is studying e to power z, a complex number. So, let z be a complex number, alpha plus beta I. And, okay, well, as I go on, I will recall some, say, facts from complex numbers. But anyway. So, e to power z is e to power alpha plus beta I. So it's e to power alpha times e to power beta I. So the question is, well, we know what this one is because that's a real number. But this one, what is this? What is this? Well, let's say you might say, okay, what is this? Well, that's e to power I beta. But I mean, can I relate it to something that more interesting? The answer is yes, we can do that. Okay, so let me do this. So let's write down the Taylor series for e to power x. In fact, here the x is beta I. Now recall e to power sub x from Calc 2 is 1 plus x squared over 2 factorial plus x 3 factorial plus x 4 factorial. Well, let me write some of them. So this is x1 1 factorial. This is x0 0 factorial. Okay. So this is 1 plus beta I plus beta I squared 2 factorial plus beta I 3 factorial plus beta I 4 factorial plus, let me write some of them when I need them, 5 factorial plus beta I 6 factorial plus okay. So, well, let's see. I to power 1 is I squared is negative 1. I 3 is I squared times I, which is negative I. I4 is I squared, which is what? Then I5 is I times I4, which is I. So, and it continues. So I6 is negative 1, I7 is negative I8 is Y. As you see, it has a period of 4. So it repeats itself. And that is, in fact, good for what we're doing. Okay, so let's go here and well, I have up to 6, so well, I know what so erase them. So this will be 1 plus beta I. This will be I squared is negative, so it's minus beta squared 2 factorial. Then this is I3 was I squared times I, that was minus beta 3 factorial times I. Right? I'm going to see that was I3, I2, that's one. Okay, so, and then 4 will be plus beta 4, I4 was 1 over 4 factorial. Then 5 was like I1 plus beta 5 factorial I minus beta 6 factorial plus 1. So let's put them together. Yeah. So that is 1 minus 2 factorial plus. But if I convert it, plus. That is the real part of this, and the imaginary part will be I times beta minus beta 3 factorial plus beta 5 factorial. If I continued, I would get beta 7 factorial plus dot dot dot. Okay. Now again, going back to Calc 2, this guy here is in fact cosine beta. That's the Taylor series for cosine beta. And this one is sine beta. Okay, so what did I find? I just found this, a nice formula for this. So let's go back here. I found amazing, nice. Okay, so this is e to the power alpha times cosine beta plus I sine beta. Okay. So, let me erase this and okay, so e to the power z is that thing. Now, well, this is just a side. Maybe you remember this formula from pre-calc or college algebra. I don't know when. Remember this formula that when it's raised to power n, that's cosine n beta plus I sine n beta. There are different ways to prove this, but one of them is this. We can say, okay, we know that this is e to the power I beta. So I'm finding e to the power I beta to power n. And that's e to the power I n beta. And by definition, this is simply cosine n beta plus I sine n beta. So that formula from pre-calc to more, that was in fact, you can easily prove it using this fact. Okay. So, I need another fact to start solving the equation, or let's say start plugging in a function like that and see what happens. So, another fact. If y, let's call it something. So if y equals y1 plus I y2 is a solution, then y1 and y2 are also solutions. Okay. So if I have a complex function like this, that's y as a function of t at time, and that has two parts. So if one of them, if the y, which is a complex function of this form, is a solution, then each one of them is a solution separately. So let's see. Let's try. So I have y, a, y double prime plus b, y prime plus c, y equals 0. That gives me a, y1 double prime plus I, y2 double prime plus b times y1 prime I, y2 prime plus c, y1 plus y2 equals 0. So let's regroup them into, it's as real and complex. So the real part will be a y1 double prime plus b y1 prime plus c y. That's the real part. And the imaginary part is this a y2 double prime plus b y2 prime plus c y2 equals 0. Now from our knowledge on complex numbers, if a complex number is 0, then both real part and imaginary parts should be 0. So this gives me this. So both of them should be 0. A y1 prime and b y1 prime double prime plus c y1 is 0, and this one is also 0. A y2 b y2 plus c y2 equals 0. And that's what I claimed. Y1, Y2 are solutions. So this means that they are solutions on their own. Okay. So these two facts will help us solve this equation effectively. Okay. So let me erase all these things. Okay, so I have a y double prime plus b y prime plus c y equals 0. And I said maybe a function of the sort e to power some z times t, say, is a solution. So let's assume that e to power r t for r equals alpha plus beta I is a solution. Now one might say, why I didn't multiply this by some k? Now I can multiply this by k, but then when I plug in, I have a k here, another k here, another k here, and the k's cancel out with 0 on the other side. So there's no reason to put a k here. Okay. So plugging in the solution, I mean the equation, I will get A. The second derivative is simply, first derivative is r, then r squared e to power rt, right? Then b times r e to power rt. Then c e to power rt is 0. So this, if I regroup, ar squared plus br plus c e to power rt is 0. Now this is not 0. E to power rt is not 0. Like e to power anything that has like a real part and imaginary part, and so that's not 0. In general, say, but so this should be 0. ar squared plus br plus c is 0. Now what is this? First of all, well, I know what this is. There's a quadratic equation, but what happened? So this is what happened. I assumed that e to power rt is a solution. Then I said, okay, if that is a solution, it should satisfy the equation. When I plugged in the equation, I came up with this. So it means that if e to power rt is a solution, then r should satisfy this equation. Okay, so let me write this in red. This means that if e to power rt is a solution, then ar squared plus br plus c should be 0. Okay? So if this is a solution, then this should happen. Okay? So let's see what we can get out of this. Okay, let me erase this thing, all these things here, and let's write down the equation. So I ended up with ar squared plus br plus c equal to 0. That's called characteristic equation. Characteristic equation. So how many cases do I have when I solve a quadratic equation? A quadratic equation can have two real solutions. It can have two complex conjugate solutions, or it can have one solution repeated twice. So this has 1, 2 real solutions, 2 is 2 complex solutions. So let's call this R1 and R2. Right, so that's R1 and R2. This one, 2 complex solutions will be something like that. So it can be alpha plus beta I and alpha minus beta I. Remember, they are conjugates. The solutions, the complex solutions are conjugates. And the 3, 1 solution with multiplicity 2. So what we call this just R, right? There's no R1 or 2. So these are the 3 cases that we encounter. And we have to study these cases separately. Now, before doing this, we can, let's talk about, let me, Yeah, and also that was in fact some introduction, and then in next sections we will discuss each one of them separately. But there's also something else that I should mention. In fact, you might say, how do I know that an equation like this, a second order equation, has a solution? Now that goes way beyond the scope of this course, but I will just write down the theorem for you, which says, which gives you some idea that in fact solution exists. You can guess from here that, well, here is that, but the number one, the first one was R1, R2, so it means that there are two solutions. The other one also, there are two solutions, and the third one is 1, so you might say, gee, maybe that's just 1. But we will see. All of them, there are two linearly independent solutions, and we will find them. So this is the theorem, and existence and uniqueness theorem. Existence and uniqueness theorem. But we can, well, this is for the general case. It's not for constant coefficient. For constant coefficient, if we can find solutions and then we just say, okay, we have a vector space and this is a vector subspace, it is not three-dimensional, so it may be two-dimensional, and if we can find two linearly independent solutions, then that's it. That is the solution space. And so this is general. This is not just for homogeneous one. So consider the initial value problem. So the initial value problem, let me see the book uses the PDT balance. PQ, y double prime, PT y prime, QT y, GT. And when it says initial value problem, so we are given the value of the function at certain point on R. Now usually you are given y at 0, because as you see I'm using t as free variable, and t stands for time. I'm not saying it's time all the time, no, but most often these equations involve physics, and that's time in fact. So let me see y0 and y, okay. So the initial values are y at the 0 is y0, and the y prime at the 0, y prime at 0, let's call it just y prime 0. So these two are constants. Right? So these two are constants, like a and b. Now the book uses y prime and y. Where p, q, and g are continuous. And then open interval y. Okay, so if the coefficients are continuous on an open interval I, then this problem has interval that contains t0. But I guess the book doesn't use 0 here. The book uses t0, so it doesn't have to be always 0. That contains t0. Then it has a solution when it has exactly one solution, y equals some function of time, which is continuous on that open interval. No, it doesn't say that. So the solution exists on okay. Now the solution should be continuous because we are talking about its first and second derivatives. If it has first derivative, then, but we will see some other things that happen now. Okay, so this is in fact the existence and uniqueness. Now, existence is when it says there is a solution. Uniqueness is when it says only one, exactly one. So this is uniqueness. If it says exactly one, it also includes the other one, which is it exists. Otherwise, we can talk about exactly one. It doesn't make sense. So that is okay. So let me see this section with some. Well, let me stop here, and then next time I will continue with differential equations. Now these are in fact different sections, so I just jumped from section 1 to section 2, and I will discuss some other things next time. Okay, so see you next time.